So yeah, as Nicola said, I'm a research scientist at the Wikimedia Foundation. And for those of you who don't know, the Wikimedia Foundation is a non-for-profit organization operating Wikipedia and sister projects. So as researchers there, basically we take care of innovative technologies, machine learning technologies to improve readers' experience so that you can find the content that you're looking for, and editors' experience so that they can add content to Wikipedia more easily. Now, my background is computer vision. I was born and raised in the multimedia and computer vision community, and then after my PhD, I met these fantastic people from the computational social science background, and they opened my mind on how much computer vision would be helpful to help social computing research. And so what I'm going to show today is a little bit of history of computer vision. So we're going to see how we got until here. It's going to last about 10 minutes. I'm not going to go through all the details, but it's just to give you an idea of what happened before deep learning. And then, depending on how you feel, we can have a shorter or longer hands-on session with some very quick and dirty code that you can use to classify, to basically annotate images at scale. And then if we have time, and again, depending on how we feel, we can then talk a little bit about previous research from our lab, from my research and from other people about how computer vision can help computational social science. All right? So let's start. I think Andreu gave an amazing overview of what computer vision is yesterday, so I'm not going to go into the details. He actually made my life much easier because I don't have to explain so many things today. But basically, yeah, machine vision is that branch of artificial intelligence, designing technologies to teach computers to tell what they see, right? And I don't know how many of you know that, but actually computer vision was born as a summer intern project at MIT Media Lab, not Media Lab, Intelligence Group, Artificial Intelligence Group in 1966. So it was supposed to be a 3-month project where students have to design technologies to basically help computers tell people what they see. They clearly underestimated the complexity of the problem, right? So this was 53 years ago, and it's still, in some parts, computer vision is still an unsolved problem. However, we did a lot of progress throughout the year. So this had the contribution to start an entire research field, which is amazing, right? And so throughout the decades, scientists have started developing more and more intelligent systems to expose image information. And the problem was that the pixel information was so redundant that basically computers cannot extract anything from raw RGB values. And so slowly they started designing these ways of summarizing the image content, what we call image features, that are nothing but image statistics summarized in a few numbers. One of the most popular image features in the early days was in the 70s, it's not an image feature, it's just a technique to extract the edges of the image. So essentially, those areas where the signal is changing abruptly, these are high frequency areas in the image. So basically, by extracting the gradient of the image, you can expose the edges. And these are the areas in the image that contain the most information, and so that they can tell us a lot about the shape and what's in the image. And then throughout the years, image statistics became more and more complex and more somehow interpretable. So, for example, Harlick in the late 70s designed these texture-based features where from the raw variation of intensity, it could say, oh, this is a complex image, this is a homogeneous image, this is a highly entropic image. These kind of things now sound very easy to you, but at that time, they didn't know how to extract these simple words from the images. They were just pixels, right? Just dust that nobody could understand. And then let's go forward. So in the 2000s, we see some first major progress in intelligent computer vision technologies. And so we actually thought we were very, very close to solve the problem at that time, but we were very far. So two are the major, I would call them inventions of the early 2000s. The GIS descriptor, again, from MIT Media Lab, Antonio Torralba, basically this was a way to summarize the whole shape of a scene by quantizing the Fourier transform in a way that can somehow get some informative information about the whole content of the image. So it was very useful to distinguish between, say, outdoor and indoor images, these kind of things. And the other one, at a local level, is the SIF descriptor. The SIF descriptor was basically first identifying the corner of the image. Again, even more than border, those are the areas of the image that contain a lot of information of what the shape looked like. And then it was a very smart way to summarize the content of this corner. And so when you aggregated all these points and these corners, then you could have a dense representation of the image. Now, essentially, what were we doing with this image in order to, for example, classify the word? Like every supervised machine learning model, we were learning by example. So if we had to design an image classifier that would distinguish between class A and B, we would first obviously take a lot of images from class A, a lot of images from class B, characterize them according to features that we were deciding. So for example, we would say, oh, I think that to distinguish between these two classes, as scientists, I think that color distribution and shape distribution is the best. So I'm going to summarize each image into a few numbers based on color and shape, and then I'm going to teach a machine how to distinguish between class A and B based on these characteristics, right? And so let's go a bit vintage. This is my first paper. It's not so vintage, it's 8 years ago, right? So ignore the rest, it's not important. What you have to see is the accuracy on the test set. It's extremely low. So we are talking, this is a data set of 20 classes. We're talking about not even 30% of accuracy. So basically, 70% of the times we were classifying the image in the wrong way. But still, we had a marginal improvement over the state of the art, and so this was publishable material. And this went on and on for many years. I was just right at the end before that deep learning revolution. So what happened with deep learning, and what Andreu explained very well yesterday, is that essentially, with deep learning, we don't need to specify as humans to the machine what the machine has to look at to distinguish between class A and B. Basically, the machine is learning by itself what is the right summary of the image that allows the machine to distinguish between these two classes or n classes without us having to impose some human language into the machine. And that is the reason why it works so well. The numbers that the machines extract from the images don't mean anything to us, but it means they mean a lot to the machine that is able then, to talk to itself and understand what's in the image. And so that's what made the deep learning revolution so powerful. Actually, deep learning is not a new concept, but it's an evolution of neural network that were around for many, many years. But when applied to images using convolutional layer and given the computational power available in the early 2010s, then it made this deep learning revolution possible. And so when I started my PhD in 2010, basically, we were struggling to teach computer how to distinguish between birds and airplane. They were the same thing, right? They were basically black dots or white dots on a blue background. And then we see here that basically in 2012, we have the first deep learning paper, and then we see the evolution, the number of papers in computer vision is growing exponentially. This is just 2017. This year at CVPR, the main computer vision conference, there were, I think, 6,000. It's a festival, right? It's like, whatever, punk rock festival, I don't know. So talking about CVPR, so remember we were not distinguishing birds and airplane 9 years ago. This is the best paper from 2018. Basically, given a video This method is able to understand 25 different levels of semantics from each keyframe in the video, all right? So not only is able to automatically detect the objects in the image and the scenes in the image, but is also able to, of course, extract edges and all these kind of things, understand the 3D depth from a 2D image. This is a very complex task for computer vision technologies. What else? It's able to segment it in a very, very sharp way, and also attach label to each segmented object. So, you know, we're talking about really, things change massively. And so I think, you know, this is the beauty of science. For years and years, we were looking at the problem in a different way, and then we just, one or two papers in 2012, we are now, I mean, the whole field changed completely. While the focus before was on the interpretation of the image, now it's about designing an entire architecture end-to-end to understand the image. All right, again, Andreu made my life much easier because I don't have to talk about why do we care about machine vision in social computing. Now, the point is that now these technologies work very well, so we can actually apply them in fields that go a little bit beyond computer vision. So computer vision scientists, basically the field aims at improving accuracy all the time. But in this, these technologies can be used to actually understand people and society at different level. Now, one problem of these computer vision technologies, and one problem of images in general, is that while text data is made of words, and therefore it's somehow self-explanatory. So when you analyze text, you can automatically, you can, for example, automatically understand what are the main words that characterize X or Y. For images, this is not the same thing. So first, we have to make images speak, and then we can use them to, in say, computational social science settings, right? Because if we just use images raw, we will never know what the content in the images. And so what we are going to look at in our hands-on session is essentially a way to extract interpretable features from the images, so that basically you can, given an image, automatically describe it with the words that you can then reuse in your social computing research. So you have any question on this part? If not, we can go to the, let's just go to the hands-on session. Let's see. All right. This is the best I can do, so I hope it's fine. All right. So I don't know. In the next maybe 20 minutes, depending on how good we feel, 20, 30 minutes, I'm going to show you what I prepared for you, which is essentially a Python notebook containing a set of quick and dirty scripts to extract images, annotations from images. So these features include color distribution, sharpness, so some edge information, information about faces, and information about objects. This notebook is very much plug and play, so you don't really have to understand the theory behind it if you don't want. You can just take some of this code, repackage it, put it in a loop over all the images in your repository, and you will be able to annotate images at scale. I was not able to prepare a very fancy virtual machine, so if you want to run this code, you have to install your some libraries, including TensorFlow and OpenCV. And we are going to use some external APIs, and so I will ask you if you want to use them to generate your own API keys. I would love to share mine with you, but they are going to block me if we all use my API keys at the same time. So in the repository that you have there, you don't have my API keys. All right, so let's see. The first, this is not super good, but let's see. Okay, so in the first bit, we just import some libraries, basically traditional, whatever, Python libraries that we often use in data science. And then OpenCV, that is the historic library for computer vision that we used to use with C++ back in the days. It's now available for Python. There is a package that you should use for Google Vision API. And then I put in the repository everything that you need to run Face++ library. Let's see, and then there is another library that I prepared for you to extract objects using TensorFlow, so you don't have to worry about anything. And then there are some API keys and initializing context that you just have to replace with your stuff. So let's run this. Next, these are just functions to plot images. Don't worry about this. So the first bit is about extracting color distribution. I think it's useful for those of you who are working on Yelena's project on images in health spaces, and for those of you who are working in computational aesthetics, and probably also the Wikipedia people. So basically here, again, we want to extract color distribution in a human-readable format, right? We don't want to have, oh, there is 20% of green, 10% of red, and 30% of blue. We want to have real colors like red, blue, green, etc. So we are going to use OpenCV for this purpose. OpenCV reads an image in the RGB format. RGB color space, I think do you know what RGB is? Yes, very good. I don't have to specify it. So we are going to first read the image. Do you know who this person is? Very good. Can you explain? Feifeli.
Okay. Feifeli.
Do you know who she is?
She's the professor in Stanford, and also she's the very famous person in computer vision or anything related to AI and.
Yeah, so she's one of the reasons why now computer vision technologies work very well. So she's the head of Stanford AI lab and one of the main figures in this area. Okay, so we're going to use Feifeli image.
She ran a dry cleaning store to do it.
What?
She ran a dry cleaning store to do her data set because nobody believed her.
Yeah, it's an amazing personality. Also very nice personal story of in the US, so a very nice character. So OpenCV, okay, let's skip this part. So basically, the whole point is the RGB space is not exactly what we're looking for because RGB is not very interpretable, so we're going to convert the image into HSV. HSV means hue, saturation, and value. I don't know why they call it value. This should be brightness, but they call it value. So hue is the color tone, saturation is how pure the color is, value is how bright the color is. Now hue is a value that goes from 0 to 136, where 30 is orange, 60 is yellow, etc., etc. And so basically we can just quantize the hue channel to understand the dominant colors, right? So I'm going to skip this part. This is how the hue, saturation, and brightness channels look like. I don't think we care about this part. So basically, the output of this step is a color dictionary for each image, where you get the color distribution over the main color of the hue wheel. And then you have also, if you want to complement, you can do the same for hue, for saturation and brightness. Okay, this is just to show you that if you change the value of the hue channel, you can basically rotate everything across the hue wheel.
Question?
Yes.
If you quantize them into these color names, you get some buckets where there's a lot of colors we humans could perceive in one name, and then all the other names are basically we don't give a shit about, right? Is that true?
Yeah. So there are for this purpose, I just quantize it in 12 equally spaced buckets. But definitely, if there is an expert in color perception, they can tell you what is the best spacing. So you just change the dimension of the color bins.
There's no standard solution for that issue.
There's no standard solution. I mean, the standard solution is go this way. You just, computer scientists, whatever. We divide by 12. That's fine. All right. Okay, I'm just reading another image. This is from the Holy Fests. I hope you all know what the Holy Fest is. Otherwise, you have people who can explain. Okay, the point here is that also the saturation and the brightness channel are important because essentially they can tell you a lot about some aspect of the image. So, for example, the holy picture is much brighter and much more saturated, and you can capture this using just the average of the saturation and brightness channel. So this is basically this tells something about, I think, sentiment and general atmosphere of the image. Maybe I can skip sharpness. This is for the people who are doing computational aesthetics. This might be helpful for you. It's basically, this is a feature that tells you how well defined the borders of the image are. And so if you have something that is out of focus or there is some movement, you can capture this with the sharpness feature. Nothing so interesting. So let's talk a little bit about faces. I think this, some of you might be interested in detecting faces in images. So why do we care about faces in images? There is a ton of literature now in computational social science showing the importance of images to essentially characterize online population. We also, so there is this famous paper from Saide, which is actually testing that online crowds are very much attracted by faces compared to pictures without faces. And another number of papers that actually shows you how much faces are important to tell about the whole intent of the image and about the user who was in the picture, the user who uploaded the image, etc. So in order to extract information about the faces in the image, we are going to use Face++, which is this API that I use sometimes. There are open source version to do all this, right? So here we want to detect a face, understand whether the face is from the gender of the face, the age, and the position, etc. There are open source libraries to do this, and I can point you to these libraries if you're interested. There are just too many, so I thought Face++ for the purpose of this week was maybe more interesting. One problem of Face++ is that while it works somehow well in certain settings, it has been proved by this work. Is called Gender Shades from Timnit Gebru from Google AI, that it happens that on images of people with darker color skin, it's not able to detect the gender very well. So this is due to the fact that they don't have enough data, enough balanced data in their training set. So just be careful when you use this, these technologies, that you always have to double check that they are not super biased. In general, whatever technologies you use, I suggest you test on the Gender Shades library. No, it's a data set, it's not a library. The Gender Shade data set allows you to test for face detectors on a balanced data set where it is balanced across different color, skin color shades. So I think this is becoming more and more important in the computer vision community, so just be aware of that. So you don't, if you have API keys for Face++, you have everything you need in the repository to run the Face++ API, so you just need to run the API.detect function. Someone was interested in body pose estimation yesterday. I don't remember who. You and you. Good. So Face++ also has a body shape detector, and it gives you some information about the pose, etc. You just have to basically follow this link and change the API request URL in the faceapp.py file to get this information. Here we focus on faces, but there is a body version of the face detection. Okay, so the API.detect, given an image, returns a dictionary with a bunch of things. I think the most important field is the faces field, which is a list with a number of elements equal to the number of faces detected. Here in the Feifei image, it detected 2 faces because it's detecting also the face in the background. So what we get here is, for example, for the first face, which is the man in the background, it detects someone whose age is around 56, gender male, with dark glasses and who's not smiling. It's also giving you, this is important if you want to do some other processing of the face area. It's giving you the bounding box, the coordinated of the top left corner, width and height. And so, okay, so, and also the second face is a Faye face. Estimated age is 27. I think she would be very happy to know that she looks like, she looks very young, but she's not so young. And so yeah, she's smiling, etc. So yeah, this is face was passed is reasonably useful. There is also an ethnicity field that I explicitly didn't add because it doesn't work very well, and I didn't know here. It might become offensive for some people. In general, I don't know. The boundaries of ethnicity for me, they're not so super clear, so I explicitly excluded that feature, but just be aware that you can also detect ethnicity of the face if you want. All right, now beyond faces, we have, yes?
Just a question.
Yeah.
Do you can get estimates from this library about how sure you can be about these estimates?
Yes.
Credibility intervals?
Yes, look, you have...
For the age, so the computer says, yeah, I believe it's 27, but I'm not very sure about it.
There used to be, I think they might have removed it.
Okay, but you can get it out of the library.
Yeah, yeah. So you can get something. So for example, for a smile, you can get this. But there used to be something similar for gender and the other properties. I think they removed it in the meantime. But maybe we can look better in the dictionary, in the output dictionary, maybe in another field. We can find the confidence scores. Yeah. It's not, I don't know why they removed it here. It's just maybe they changed the output, so I don't know exactly where to find it, but there used to be. Yeah?
Does it include any facial expression?
So there is just the smiling feature, so whether it's the person is smiling or not. If you
can extract facial expressions from the face.
You can extract facial expression, so you can use other libraries to do this. You can, for example, Google Vision API gives you a little bit of that, but you can use, for example, some from the face. You can use once you have the face image, you can use some other TensorFlow libraries to detect facial expressions. But this is you did it? There is the function.
You have some
Okay.
other API, but it's still face++, where they give you a score for happiness.
Is there? Okay, maybe I didn't see it. So yeah, but you see, it's I didn't know because it's maybe I knew something that I haven't. Yeah, I haven't seen it. So yeah, it looks like you can, which is great. So you don't have to pay for Google Vision. That's good. So let's see. Okay, beyond face. Do you have any other question on the face aspect? It looks like we're good. Beyond faces, you can also detect everything that is, sometimes you don't have faces, sometimes objects in the image plays an important role to characterize what's in the image, but also, everything around the image, right? And so there are, again, two ways to do this. One is the open source way, which is we are going to see right now. And the open source way uses a TensorFlow-based library that is, so a TensorFlow-based classifier that is trained on ImageNet. So yesterday ImageNet was mentioned, and actually Faithful is one of the people who initiated ImageNet as a concept. Is I think probably the largest image database available, and it's the visual mapping of WordNet. If you know about WordNet, ImageNet is the visual complement of that. So it's structured in a hierarchy, and every concept has a bunch of images attached to it. And so ImageNet is used as a benchmark for computer vision classifiers. And the problem is that this benchmark and in general the models that you find available, they are trained to detect 1,000 classes of ImageNet. And these 1,000 classes are not exactly reflecting the general distribution of objects in the world. There are so many dog breeds and there are no like things about people, so it's not perfect. I put the list of objects there for you to check. There is something, it's definitely not perfect. If you have a project about dogs, that's going to be amazing, but sometimes it's not, yeah, it's a bit limited, but it's what we have right now. So this is the architecture that we're going to use as Inception v3. Just forget about everything. The input is the image, the output is a vector of 1,000 elements, and each element is actually the probability that the image belongs to one of the 1,000 classes. So this is the output of the network. So the network is not giving us a class, it's giving us a probability of belonging to one of the 1,000 classes. So typically what we do is that we take this 1,000 vector, we rank it in terms of so we rank it. So at the top of the rank we have the most probable classes, and then we take the say top 5. Then from the top 5 you get rid of the ones where probability is very low, and you look at the top one. I didn't know what this thing was, but apparently it's the breed of the dog. This is the only thing that can detect in the image. So as you can see, it's not perfect, but this is what we have. And for another image, like for Serena Williams, from this image, you know Serena Williams? Yes, yes. I don't know, I ask. So the only object in the image that is not Serena Williams is a racket and a tennis ball, and actually able to detect it very well. So if you have installed TensorFlow version that I mentioned in the requirements, you can just run this very easily on your images. You don't have to worry about anything. All right, last bit is about Google Vision API. So Google Vision API allows you to detect objects and a bunch of other things. It works very well with some limitations that I'm going to talk about. First limitation is that if you have a free trial, you can classify only 1,000 images, and then you have to pay. Not much, but when you have millions of images, it becomes a little bit expensive. And the second, and this is something the community again is aware, is that because it's trained on unevenly distributed data around the world, for images of the same concept coming from 2 different areas of the world, we see a bit of difference in the way they are classified. So a marriage coming from an African country is classified as ritual and ceremony, while a marriage coming from a Western country is classified with a bunch of very detailed classes from the wedding sphere, right? Like cutting the wedding cake or whatever, wedding dress, these kind of things. So this is something I tried a few days ago, right? It's not a common thing, but actually community is aware, and actually Google started this inclusive image challenge this year to overcome this underrepresentative ways of classifying the word and to make image classifier more inclusive. So this inclusive image challenge is a call for scientists around the world to improve the inclusiveness of image classifiers. Now let's look a bit at what Google API does. So again, here we are classifying Serena Williams image, all right? So you have to create whatever. This is 2 lines of code to get your image annotated. What's very beautiful, I think, about Google Vision API is that it leverages the power of the web, right? So what it does is that it's not only able to detect objects, but very specific web entities. So it's going to look at the similarity between the images and the other images in the web, and then retrieve the web entities related to the pages where these images are attached, right? So it can actually detect concepts like Serena Williams itself. It's very hard to infer this using image-only, image pixel-only detector, right? It's also detecting related concepts like Wimbledon or US Open, etc. All right, and then you also get normal objects like tennis racket, tennis ball, but also you have higher level concept like championship or competition event, sports, so it goes up in the hierarchy, so it's very, very powerful tool. Okay, you also have some face annotation, like there is everything about position on every landmark of the face, which is very nice. And at the end of this, you also have some information about the facial expressions, some information about the quality of the image, underexposed, blurred, and whether the person is wearing a headwear or not. All right. Does this sound in general useful? Yes.
So I'm still a little confused. How do you separate like what your data is telling you from what the algorithm is trained on and able to tell you? Like that's part of the issue with like, you know, you see two images in a wedding and it's not like, it's like they could be two weddings, but it's a factor of how it's been trained. And we talk about in terms of machinery bias, but I'm a sociologist, so I'm thinking how to use this like to study social situations, and I'm still confused how to separate out like data and then model.
Yeah, so in general, what the model is learning is very much a reflection of the data that you give as input, right? So if the data, if the data is somehow unevenly distributed, so if the data is taken from the visual production of people around the world, the user-generated content is not evenly generated around the world for reasons that we all know, right? I think I had a map somewhere, not here, but of where the content is generated around the world, and you see Western countries, and you see, you know, a large part of Africa where there is no content that is generated, and then you see you know, some parts of Asia where no content is generated just because of limitations. And actually, we have the same problem, for example, in Wikimedia spaces, right, where the content is unevenly distributed, and we're trying to fill this gap. So just to answer your question, I think if you want to look at this problem, the model itself is very dumb, right? So it's just learning an association between pixels and classes. So I wouldn't focus on the model very much. And most of the solutions for the inclusive image challenge are actually trying to mine data from other sources, because at the moment this is the only resource that we have. But there is an entire new branch which is about fair, accountable, and transparent computer vision that is trying to bridge this gap, and maybe we will find another way that goes a little bit beyond the data. Yes, yes. She was.
I was just wondering, so is it possible to teach the algorithm to, so let's go back to those images, right? So the one on the left it did recognize many features. Can you teach it? Because I'm thinking about my project with the Virgin Mary. There are different iterations of the Virgin Mary, like artistic expression and so on. So can you teach it?
Can you teach
the algorithm?
That these are the same thing?
Yeah.
Yeah, so once you have, so obviously you need more annotations on specific type of data coming from certain countries, right? So the reason why we know this is that I looked for specifically on the web for weddings. I think this is from South Africa, but I don't want to say something that is not right. And then I knew that those were the tags that I was looking for. So you need, at the moment, you need a lot of human in the loop. So you will need humans to look at this data, or some way of having another level of annotations on this data, so that the model can learn that these two things are the same thing. So you can, if you know that these two things are the same, these two images are about the same thing, you can teach it. But first you need to know that part. Yeah. I think she was first. Yes.
Similar question. I was wondering, how can you measure uncertainty? Because the only measure that I know is you look at your test set or your validation set, and you look at how well does your model score.
Mm-hmm.
Is there any other way to get an amount of uncertainty about the prediction of the model?
So in the Google Vision API, I cannot speak because obviously this is proprietary software. So let's see. So they are starting to develop standards that go beyond. So what you mean is like, basically we're maximizing in general for accuracy, right? So we're maximizing accuracy and looking for that. And the only confidence score that we have is whether it's accurate or not. So at the moment, there is no standard metric to have other confidence scores that are more related to like properties that go beyond this accuracy or efficiency. But the community is working on that, and there was someone yesterday who was actually, I think it was him, who was actually looking for ways in teaching the algorithm. What are the properties? Is it you? What are the, no, you behind, no? What are the properties? It's not you? What are the properties that the machine learning technologies should be careful in classifying? It's you, right? Yeah. Yeah. Sorry, I had to remember. So, I mean, there are these initiatives in the AI ethics area that are emerging right now, but as far as I know, there is some work to do in that direction. So, looking forward to your results. Yes.
So the web entities you get back.
Yes.
/m/ they look awful like freebase IDs.
Yes.
So is that what they are?
Yeah.
Because if that's the case, then the data set that's behind it is super biased.
Okay, the answer is I don't know because this is a closed
just give
platform.
us that, and you cannot. Could you take that and look in Wikidata if that is an actual freebase ID for removal? Because it would be Wikidata, for example, right?
I'm sure it is.
It is, right? So, but
it is a freebase ID, but I don't know exactly how they generate this.
They actually do the crawl of the web.
Yeah, I think I imagine it's like that.
This, right?
Yeah.
So that means like all the web that they couldn't classify. So whatever comes
Yes.
out of this is as biased as freebase, which is really bad news.
Yes, I know.
Okay.
I know. So it is good for, again, images coming from certain parts of the world where we have a lot of information about knowledge represented in the web, right? So yeah, I totally agree with you. It's, I don't know. I imagine that they do it in this way, but I cannot tell you exactly right.
But it's a good handle to tackle the bias.
Yeah. Yes.
I think to go up that, and back to what I was in the data model, I think you could think about like which of these tags are more likely to be just a product of the training data and which ones might be more like generalizable. Like the head tilt, I imagine is something you could use and not just think it's an artifact of the training it was seeing. And you could actually like use it and come to some conclusions that some type of images have more head tilt than others. Like maybe, women tend to have more of a head tilt than men in pictures. And that's not just because it was trained on some data, so it knows to look for it in women more than men. But other features would be more of just a product of whatever the training was. So I think you could just think about which features you're looking for and if they are prone to bias.
It's also different in India than in the US, right?
Well, yeah, so you would think carefully about like the actual feature that you're looking for.
Yes.
Along with that, I wonder if it's possible to kind of like have, again, this is all new to me, but like kind of like a library of information of wedding in different cultures like, and then it feeds into the algorithm. And I say, okay, in India at weddings they touch the bride's and the groom's feet, which is true by the way, right? And of course it knows that by referencing this library of weddings in different cultures. I wonder if that's possible. So that way it's kind of like a quick way to identify different forms of wedding rituals across different cultures.
Adding external knowledge, I mean, yeah, it's one of the solutions. I don't work specific on biasing, so it's probably one good solution. The problem is how to ingest this knowledge into a computer vision classifier, right? So that's definitely a good option.
Just importing that information.
Yeah. That's good. Very good. So I think with this, just take this code and whatever is probably not going to work at the first run, just come to me if something is not working. It's very likely that it's not working. So just come to me. All right. So it looks like we have a little bit of time to talk about machine vision in social computing. So I think basically the idea is that I'm not going to show you plots of number of images produced every day by people around the world, because I think we've seen it enough. It's a lot, and we all know, and I think some people here know more than me how important visual communication is in these, it's this new form of communication where, a lot of people are using it. So when we are analyzing people and societies, understanding the visual production and the visual component of the communication becomes very important. And so what I'm going to show you is a set of studies that the community is doing to use images to understand people and societies at scale. So we are going to look at 4 different aspects. One is the individual scale, so it's about understanding people traits and people perception of images using somehow very controlled data set. The second one is at urban scale, and so basically using images to understand, using images geolocated in the world, in cities, to understand aspects of the city. The third is the web scale, so looking at the visual content production around the world, we can understand culture dynamics of people and how people relate around the world with images. And finally, I cannot just leave this out because I work in this. So I just want to spend some words talking about modeling with visual knowledge in encyclopedic spaces and how this has not been done. And so we should all do this, all right? That is the general message. So, all right, let me talk about the individual scale first. So there are quite a few work emerging in the recent years about understanding people traits by looking at the images they upload. So essentially this has focused a lot on personality, and basically by relating the big 5 personality scores with the image a person uploads, you can somehow automatically infer some of these traits. So these are the main references that I found. I can give them to you later. You have the slides, so I'm not going to go into the details, but I think if you're interested in these aspects, these are 2 very good references for that. One work that we've been doing in the past with my former colleagues is also about not only understanding personality traits, but also understanding lifestyle traits. So we did this work with the social psychologists from University of Texas to basically given the faces of the people going to a place, we could automatically understand the atmosphere of that place just by looking at the faces, right? And it works fairly well because as you can see, your way of presenting yourself in online spaces kind of tells a lot about your lifestyle and the places where you go, especially in certain social media. So I can give you more details about this work, but it was, I don't know, a nice work. Another way to understand people traits and how people relate to images is to not looking at their content production, but looking at how they perceive images, so how they annotate images. So if we have data set annotated by people according to certain properties, and we can extract features from those data sets, then we can relate these features to people annotation and understand how people perceive images using a computational approach. So the work that I'm going to show you is from the computational aesthetic field. You have some people working on this in these days, so maybe you're interested in this. So basically, this is about designing technologies that given an image can say whether it's high quality or not, whether it's beautiful or not, right? And so the specific work I want to show you is about computational portrait aesthetic. Basically, these are models that given digital portraits can say whether they are high quality or not. Obviously, we are not looking at the beauty of the person depicted. We are looking at the beauty of the image composition, knowing that there is a person in it. And the reason why we do this is I don't know how many passionate photographers we have out here, but if you take pictures of people, you follow different rules compared to if you take pictures of everything else. And so dedicated rules for portrait photography has to be mapped in the computational world as well. So what we did here is that we had this data set of 10,000 images of people annotated in terms of quality by professional photographers. And from these images, what we did is that we extracted a bunch of features inspired by portrait photography. So we went and read portrait photography rules, and we map each of the rules that photographer follows to shoot good portraits into a visual features, into a few numbers that somehow summarize some stylistic feature of the image. For example, if you take pictures of people, you have to know that the eye sharpness is very important. And by using computer vision technology, you can isolate the portion of the image where the eye is, and then you can compute the gradient, what we saw before, the edges, and compute how strong these edges are, so that you can compute a general feature that can tell you how sharp the eyes in the images are. And then we also add a bunch of demographic features to see how biased these photographers were on the subject when they were assigning a quality score. And so by correlating each of these features with the quality scores that are assigned by photographer, we could understand from using a computational approach what makes a portrait beautiful for this photographer. And so we saw that there are some features that are positively related, and these are all related to technical things like the sharpness of the eyes and contrast between foreground and background, etc. Some features, they are negatively related, and there are some features that have absolutely no correlation with the portrait quality, and these are the demographic features. So no matter the age, the gender, or the race of the person depicted, if the photography is well done, then the people would annotate it as beautiful, right? So this is a way to understand, also talking about the bias, this is, for example, a way to understand how biased your data is towards certain specific demographic categories when you're talking about these intangible properties, right? Okay, so let's go a bit at a higher level and let's talk about urban scale. You take pictures of cities probably every day when you are in your city, or you hang out and you are a tourist, and you often geolocate it, right? And when this is aggregated among many, many people in online spaces, then you can mine some patterns about the city looking at the images that are produced in certain areas of the city. So if you're interested in looking at image content production, image-based characterization of the city using computer vision, I think deep learning in the city is one of the Bible that you have to read. This is a ECCV 2016 paper where basically just using Google Street Map images annotated in crowdsourcing. Is it annotating? Yeah, I think they're annotating crowdsourcing. So annotating crowdsourcing for 6 properties of the city, including safety, wellness, beauty, etc. They can automatically infer at scale from the city what are the most safe areas. I think then the paper focuses on safeness only. Safe area, the most wealthy areas, and so on. Just by looking at Google Street Map images and trained on crowdsourced annotations. So in general, if you like these things, I think Cesar Hidalgo group is a very good group to check out because they are doing a lot of these kind of works. So when I was working at Bell Labs with Luca and the other people, we also work a little bit in this subject. And instead of focusing on specific, safety or wealthiness properties of the city, we focus on the intangible notion of ambience. The ambience of a city or a neighborhood is that feeling you perceive when you walk into a neighborhood. You might say, oh, this is creative, this is lively, this is boring, this is quiet, etc., right? And so as you can see, ambience is a very intangible property of the city, and so quantifying it is not an obvious task. There have been some attempts in doing this, and our version of this attempt is to look at trying to classify ambience in the city and map ambience in the city using the images geolocated in the city. So what I'm going to explain is a part of a larger study that we published last year at the CSW. And it's about using images to understand, to explain many things about the city. What we're going to see today is how to use images to map and classify urban ambience at scale. So the first step, if we want to do this, is to first systematically understand what ambience is. So we created this taxonomy of urban ambience terms, and Luca is going to talk a lot about how to create this taxonomy, so I'm not going to spend any minutes on that. It's basically, this is a grouping of terms that we generally use to talk about places in the city, like, I don't know, lively, noisy, etc., grouped into ambience dimension, like joyful, alternative, fancy, etc. So this is just purely text-based. And the reason why we need this is because we are going to look at picture tags and trying to see what are the ambience dimensions related to these picture tags. So we focus for this study in the city of London, because it's beautiful, because it's a city where we live and that we know, and a city that we love. And so what we do here is that basically we download from Flickr all the images that are geolocated in the city of London. And then for each neighborhood, we then look at the groups of images that are geolocated in that neighborhood. We look at the image tags, so those tags that you assign to images when you put on the web. We look at the image tags related to these pictures. And then we count how many of these tags fall into each of our ambience dimensions, so that we can then quantify the ambience dimensions according to the frequency of those tags at a local scale, right? So just to give you an idea, sorry, Diego is writing. So just to give you an idea, this is, I don't know how much you can see, but this is a map of London. These are boroughs that are like gigantic neighborhoods. You might not know London, but you might have heard about Camden Town. There is the Camden Market that is very punky. It's very nice. It's very punky kind of alternative place. So thanks to this automatic tagging of the city, we can automatically score the ambience of Camden Town as being alternative, stylish, and lively. There is a distribution over the ambience wheel and some visual examples. Again, Westminster is where the British Parliament lives. And so it's a very popular neighborhood because it's very touristic. It's cosmopolitan because it's very touristic. And it's also alternative because there are a lot of demonstrations there. So this is, for example, it's not super precise, but you have a lot of images from demonstration coming from Westminster, especially Brexit demonstration in these days, I would say. Yes. So I think this is a nice way to basically characterize the city in a bottom-up fashion. So instead of having someone saying, oh, this neighborhood is like this and this neighborhood is like that, we leverage the content production at a local level, and we can basically map the perception of people at scale by looking at their visual content production. Okay, this we saw it. Let me go on. Yes. So now the problem is, and for those of you who has worked a little bit in computer vision, is that not all images come with tags, right? And actually, many images don't have tags. So what do we do for neighborhoods where we don't have tags? What do we do? Well, still, we don't have tags on images, but we do have images. So we can basically use the content of the image to automatically classify the ambience of the neighborhood. And so basically using computer vision, given the groups of images coming from a neighborhood, we can automatically score in terms of ambience. So this is exactly what we did. So given this group of pictures, a group of pictures from a neighborhood, we extract using, I think it was ImageNet, I don't remember, the distribution of objects of these concepts in the city. So basically how many, I don't know, people, streets, buildings, etc. you have in this group of pictures. And then for each neighborhood, we also have an ambient score so that we can then build a model that can associate presence of these computer vision-based mind object and the ambience, so that for a new group of images from a neighborhood, given the pictures, we can automatically score its ambience. Does it work? Pretty well. So the accuracy on the test set is pretty high, and it works better for ambiences that are visually uniform across neighborhood. For example, quiet neighborhoods are in general residential neighborhood with green areas, etc. So they're very easy to recognize. Creative neighborhoods, by definitions, are visually diverse, so they're a little bit more difficult to classify just using images. Again, because we use interpretable features, we were able to associate ambiences with the things that are found in the image. So we found pretty obvious association between, I don't know, joyful, quiet neighborhood associated with outdoor spaces and greenery, cosmopolitan associated with architecture, these kind of things. But this is just to have a complete, end-to-end model that we can explain. All right. If we don't have any question on that, I'm going to talk about the next bit, which is going, yes?
But, so all the websites work with what resource? Flickr?
Flickr. Did I say?
Flickr.
Maybe I didn't say Flickr. It's Flickr.
And you think it's representative? Because tourists take a picture always from the same location. The selection is really based to the mood of the tourist. So what you have in Flickr is really more representative of the picture from the city.
Yes.
It would be much better to have the collection of pictures that come from Google Street View to really say something more about the mood of the city. No?
Yes.
Besides, you need a point of view, a camera that is objective. Not give the camera to a person that's looking for fun, they're looking for beautiful landscape. So otherwise, you don't have a correct representation of the city.
That is a very good point. So we try to control for that. So we try to take, say, one image per user and then remove the event effect by reducing, taking just an equal number of images per day. The viewpoint we cannot change. The problem of using Google Street View would be great, but you don't have annotations on Google Street View, right? So this was very handy because we had also the impressions of the people, so we had the tags, right? And that's the reason why we preferred Flickr over Google Street View, because to get that annotation at that scale, you had to do a massive crowdsourcing experiment on Google Street View images. But in general, yes.
But why do you need annotation?
The annotation is taken directly from Flickr, from the tags.
Why you use the annotation and don't some unsupervised learning to identify the action from the picture?
So how do you do unsupervised learning, and then how do you then annotate the neighborhood?
In the picture, action, situation, crowd, also. It's a very good technology to identify what's going on in your picture, trained
Yeah.
by other data sets. But yeah.
Yeah, so that is a good point, but then we didn't have the ground truth and ambience scores, right? So the point of having this is that we have a nice way of associating the tags with the ambience scores. But I totally agree with you that it's a little bit biased. At the same time, Google Street View is just showing streets, right? Part of the ambience of the city, and this comes from ambience literature, comes also from the people and the places that you find in the city. And in Google Street View, you don't have this. First, because clearly faces are anonymized, but then you don't have the interiors of the city. You don't have.
Okay, but
Yes, tell
do
me.
you have the authorization from the people from Flickr to be in the dataset?
These are public
No,
pictures.
it's not enough. You need the explicit authorization for each person in the picture to be part of your dataset. You know that? It's a new European Community rule.
I didn't know this thing.
Yes, unfortunately, yeah, and I really know that.
Okay, I didn't know this thing. These are Creative Commons pictures,
You
right?
need the explicit agreement from each person in the picture in Flickr to be part of your training data, to training the model too.
Okay,
No,
it's
this is a Flickr 100 million.
yeah, it's 100 million. It's a Creative Commons.
So it's a corpus that has been
Yeah.
basically published, and people agree on that because they agree explicitly.
Yeah.
But there is at the moment there is a big battle about that. So I really know that because we use this data set because it's common,
Yeah.
and all the journals around the world attack the company because they've been used without asking explicitly to the user.
Yeah.
So,
No, sure.
so I
think
totally
it's-
understand what you're thinking, but it's not true. Legally, it's not true.
Okay.
So unfortunately, it's not true.
We didn't know because
It's a problem we will discuss also tomorrow, I think. Yeah.
It's a big problem because many of the data that we want to use to train our model, unfortunately, are this big obstacle to.
Sure. Nowadays, using the data after GDPR, it's very
Yes.
hard.
this was before, and maybe we should talk offline about this.
The website probably.
The what?
Maybe the website is available.
This is a website available. Yes, you should shut it down.
Well, I don't know, but probably.
I don't know. I mean, for me, if it's yeah.
Sorry, it's my bad mood of legal.
Yeah, we talked about also yesterday about your. No, that's fine. That's fine. I mean, I think it's all interesting issues, and we also have these issues in images in Wikipedia. So I totally understand. All right, let's. I don't know how much time. Let's see. 18 minutes. 10 minutes. 15 minutes. Let's see. So one of my biggest obsessions is about understanding how cultures perceive images. I think you heard it yesterday. And this is something I've been working a lot in the past years. So there is a little bit of literature existing, even beyond Wikimedia spaces. One is on Flickr, and you shouldn't look at this because it's, again, it's again Creative Commons images. And so yeah, it's, and there is another work based on Facebook images that are trying to understand digital patterns around the world. The work, so if you're interested in these things, yeah, I can give you the references. So the work I want to show you, and I think someone will be very interested because yesterday she talked about this, is about understanding how culture plays an important role in visual emotion perception from a computational perspective. So I think you can speak more than me about how emotions are not universal, and some of it are actually depending on the culture of the person who looks at the image. And so here the work is to try and understand using computer vision how different cultures perceive images. So this is a work coming out from computer scientists. So there is all the psychology bit missing. So apologies. the point is we were all people from all around the world, and we were working on image sentiment classification. So these models are given an image can say whether it's positive or negative, joyful, etc. And so we could quickly realize that this understanding sentiment as a global notion for the whole world could not go on for so long, and that we should make this sentiment classifier more inclusive and try to make them multicultural. And by doing so, we can study the role of culture up to a certain point in visual emotion perception. So to do this, we downloaded a large data set of around 8 million Flickr images. This was 2015, okay? So please. So what we did is that we query Flickr with emotion keywords from the Platschik wheel, translating them into 12 different languages. So we could basically retrieve images from emotion bias images from 12 different language communities, right? And so for these 8 million images, we have this language annotation that we badly approximate as the culture, apologies for that, and then a sentiment annotation that we infer through crowdsourcing. I'm going to skip the details of how we annotate 8 million images in terms of sentiment, but we can talk about this offline. It's something possible, but you have to do some work around. So the first thing that we did is that we cluster images. So we generate cluster of semantically similar images by clustering the text, the metadata around the image in using multilingual word vectors. So we had this cluster of images that were semantically the same for different language communities, but that they were actually coming from different language communities, so they will look very different. So they were very visually diverse depending on the language community of reference. And also we found that for the same visual concept, different language community would in general assign different sentiment scores. One example is here, traditional clothings. Another thing that we did with this data as a higher level analysis was to extract, basically run a face detector at scale and compute simply the average sentiment of images with faces versus images without faces. And what we found that consistently across language communities, across culture, images with faces had a more positive, and if not more positive in general, very more polarized sentiment compared to images without faces. And this is in line with a bunch of literature that we read from cognitive science and psychology. And finally, to have a general understanding of similarities and differences between the language communities that we had, again, I'm going to skip technical details here, but we create this language-specific sentiment classifier. So we had sentiment classifiers specific for each language community, which means that given an image, we could now detect the sentiment for the Italian language community, or what that a Spanish would give, or a Chinese would give, etc. And then, while this is per se an interesting computer vision exercise, the most interesting part was to compare this model, basically comparing the underlying data distribution in this model to detect similarities and differences between different cultures. So we found, for example, that Latin language communities would tend to have similar ways of assigning or perceiving visual emotion to images. Let's talk about encyclopedia. And very quickly, this is my job. It's basically designing machine learning technologies that don't optimize for accuracy, but optimize for knowledge equity, which is this beautiful principle that we have in the strategy of the movement and the idea organization that essentially pushes us to design technologies that break down the social, political, and technical barrier preventing people from accessing free knowledge. Basically, the idea is that everyone in the world, no matter their language, their location where they are, their internet access, their literacy, their education, they should be able to access free knowledge. Not in the form maybe that we see today in Wikipedia, maybe in other forms, but this is what we are aiming to. All right, so as you can imagine, in this context, images play an important role because images are very important tools for communicating knowledge in a very compact form in space, and it's also a very multilingual way to share knowledge. And as a non-native speaker in an English-speaking country, I can tell you images saved my life many times where I just don't know a word, they show the image, right? So because of this importance of images, and also we saw yesterday that images are very important for learning. I remove all the learning part because he explained it yesterday. Images are very important in encyclopedic space. However, we are still missing a lot of images in Wikimedia spaces. So in Wikidata, which is the structure form of Wikipedia, let's say, it's a knowledge graph behind Wikipedia. 95% of items are still missing images, and around 1/10 of the articles in Wikipedia are marked as missing images, but we might be missing many more. It's just, these are just the article for which someone looks at it and say, oh, we're missing an image, but not everybody does this, right? So there is a huge visual gap, and I am probably just going to skip all this. Basically, we don't know how to fill this visual gap, because first we need to understand how to fill this visual gap, how important are images in the context of encyclopedia, how are people learning through images. So all these things we don't know. We then need to quantify this visual gap. It's not enough to say 95% of items in Wikidata are missing images. We need to know where are we urgently missing images, and who are we targeting with these images? Like, who are the people that are and what are the populations that mostly need images to absorb knowledge? All this we don't know. What else? We could, for example, going beyond aesthetic, going beyond sentiment, we could automatically use the computer vision technologies to surface from the large number of images in free repository the images with highest encyclopedic value. But how do we do this? We don't know. So there is a lot of, there are a lot of open questions. And obviously one of the questions is also, we are targeting the whole planet with our image technologies. How do we do this in the best way that is inclusive? We cannot afford, having weddings from African countries not tag as weddings and tag as ritual. This is not something that would be welcome as an effort towards knowledge equity, right? So we really need to study ways of being as inclusive as possible and understand how different cultures are perceiving visual knowledge in a different way. So with that, with these questions that I have no answer for, I hope we can have very fruitful conversations in these days, because I know you all come from very different fields. I think basically with these excursus towards the different ways of using images for studying people and society, I hope I exposed some themes that were inspiring for you. There are some themes that are very common in my research and that actually eventually brought me to the Wikimedia Foundation. And so I hope to have nice discussions with you in these days. And thank you.